Hello everyone and welcome to this session in the NPTEL course Machine Learning for Core Engineering Disciplines. In today's session, we will be having a tutorial on unsupervised learning and we will see how to implement some of the algorithms that we have learned in Python and see how they provide us insight into the structure of the underlying dataset. So let's go ahead and delve into the world of unsupervised learning through Python. The teaching assistants for this course are Dr. Manas Sharma, Shivam Chaturvedi, Mansi Lavekar and Amar Krishna Gopinath, and I thank them for their efforts. So let's go right into unsupervised machine learning with Python, and specifically what this tutorial does is it will teach you about principal component analysis or PCA, which is for linear dimensionality reduction. This is what we learned in the class. Then we will talk about k-means clustering, which is the simplest form of distance based clustering that can be done. That's for partitioning data into clusters, and we will proceed to more complicated clustering algorithms like density based clustering through the dbScan algorithm, and finally we will have a look at TSNE, T-distributed stochastic neighbor embedding, and the uniform manifold approximation and projection UMAP for non-linear dimensionality reduction and visualization. Okay. For this particular tutorial, we will work with a famous data set known as the iris data set, which consists of 50 samples from 3 different species of iris flowers to explore these concepts. If you look up online, you will be able to see the types of flowers that are included in this data set. Alright, so the iris data set contains a total of 150 samples of iris flowers with 4 different features. So the features are the sepal length, sepal width, the petal length and the petal width. Petal is of course something you may understand very intuitively. Sepal is the kind of leaf like structure around a flower, right? That is called a sepal. So you can measure the length and width of that as well as the petal. The important thing is that there are 4 features and there are 3 types of species. So this is a classic data set for unsupervised learning because it already has these 3 species identified, right? Now when you work with real data sets, you may not know how many clusters you want, so that's going to be more challenging, but for a pedagogical introduction such as this, this tutorial is sufficient. Now we import the necessary libraries such as pandas, numpy, matplotlib.pyplot and cbon and so on. Okay, and this is where we set the color palette and the style for the plots. Alright, now this iris data set is actually one of the standard data sets in scikit-learn. So from sklearn.datasets you can import the iris data set, and this will load the iris data set into this iris variable, and then through the pandas data frame command you can see what the data is. You can get the features and the so called target variable here, right, and that simply means the type of the flower. Now like I mentioned, in real unsupervised learning you may not know, right, what classes the species already belong to, and that's something for you to figure out, but in this toy data set we do know what the classes are already. Okay, so this tells you the size of the data set, so it has 150 data points and 4 features like we had discussed earlier, and then yeah, these are the desired classes that we want to visualize the data in by doing clustering, whether it's k-means or dbScan or some kind of nonlinear dimensionality reduction. Alright, so these are some first few rows from the data set. As I mentioned earlier, these are the 4 features: the sepal length, sepal width, the petal length as well as the petal width, and these are all reported in centimeters in this iris data set. Okay, so now first thing that we will do here is we will do a test train split and standardization. Remember, often that unsupervised learning is a step en route to supervised learning, because once you figure out the clusters you may want to develop separately supervised learning models for each cluster, or you may want to do some further analysis with the various clusters or the variables that arise from the unsupervised learning, like PCA or UMAP, right? So for that reason we are doing a test train split here, right? Remember, in unsupervised learning, as such, you don't validate the model as such, but this train test split is really necessary when you want to use the output of the unsupervised learning into some other supervised learning model. So now one thing to do before we go into principal component analysis is that it's most effective when we scale the features, and this is something we had discussed in class, that we want to make the mean as 0 and the standard deviation should be 1, and there is actually an inbuilt command in Python that does that, which is the standard scaler command in sklearn preprocessing, and this transforms features to have a 0 mean and standard deviation 1, and we fit the scaler only on training data to avoid data leakage, right? We don't want the scaler to scale through the test data. Alright, so these are commands you've seen already, the test train split, right? And then this is something we encountered here, the standard scaler. So that's what we are doing here. We are splitting the data first, right? You have to give the size as well as the random state, which is not visible here, but you could set those kinds of commands. The other thing is there is also a possibility in test train split to stratify the test train split. Remember, when you do classification, there are several classes. You want to make sure you sample enough data points from each class, so that is where the stratified sampling is useful, and there's a tag which you can use in the test train split to do that. Alright, so this is how you activate the scaler, and then you transform, right, the training data through the scaler. So the mean and the standard deviation of the trained data will become 0, and then you can use the same transformations, right? You will have to subtract some number from each of the data points to get a 0 mean, and you will have to divide the resulting data points by some value to get a standard deviation of 1. So those same values will be used to transform the test data. So you can see the difference in the commands here. Here we are using fit or underscore transform. So that means you use the trained data set to figure out how to make the mean 0 and the standard deviation 1, and this is simply transform, it's not scaled or transform. So here what you do is you use the transformations which were derived in the previous command and use them to apply those to the test data set. So the same number will be subtracted from each feature here, and then the normalization to make the standard deviation 1 will also be done by the same number which was determined in the previous command when we did fit transform. Alright, so this is the size of the training set, 105 data points, 4 features, and then the test set is 45 points and 4 features. Alright, so let's now come back to principal component analysis. As you would remember from class, PCA finds the directions of maximum variance in the data, and one can carry out PCA to attempt linear dimensionality reduction, which reduces the number of independent variables required to train a machine learning model for the data set. So as I had mentioned, often unsupervised learning is done en route to supervised learning. So this is again one of the useful features, that you have a less number of variables to work with, so your models can be only as complex as needed and they won't overfit the data. Okay, so the code that we are presenting here, it carries out PCA on the available data in the iris data set and produces a 2D plot of the first and the second principal components. Alright, and yeah, the number of principal components is up to us. We can specify how many principal components are needed. So this is just to refresh your memory. PCA is a dimensionality reduction technique that finds the directions of the principal components where you have the maximum variance, and then the components are orthogonal and they are ordered by explained variance. If you recall what was done in the lectures, you would remember that we discussed the concept of singular value decomposition and the singular vectors and the singular values and also the eigenvalues of the covariance matrix, which were able to tell us the explained variance. And it is certainly useful for visualization, noise reduction, feature compression, and things like this, which are quite important. Now the key concepts are explained variance ratio, how much variance each component captures, the total variance that is explained by the first n components, and how the original features contribute to the each component, right. These things, if you understand, you can figure out how the PCA has worked on your data set. Alright, so at any point feel free to pause the video and type out these commands, and the syntax of these is well available online. Okay, so we are importing PCA from sklearn.decomposition, and then we are able to fit transform again on the trained scale data, the trained scale data, and this was the standard scaler we had applied earlier, and then again we are doing transform on the test data set. So note again the difference between fit transform, which is used to find the transformation matrix, and this is something we had discussed in the class. Once you have the transformation matrix, any new point you can use that matrix to obtain the principal component. So it's important always to understand the difference between fit transform, which tells you what's the transformation that needs to be applied, and then you can apply the transformation on other data. In this case we are applying it on the test scaled data. And I'm also plotting here the explained variance ratio as well as the cumulative explained variance. So this is the explained variance ratio, and the cumulative explained variance is close to 1, right, because there are only 4 features, right. There can be only 4 principal components, and obviously if there are only 4, then if you take the total of all of them, it will have to add up to 1. Alright, so now one can plot the percentage of variance by each principal component, and that leads us to the concept of the Scree plot that we had discussed in one of our lectures, right. So a Scree plot helps determine how many components you should retain in the principal component analysis, right. And here we have shown two plots, one on the left, one on the right. You will see as I scroll down, the left plot shows the individual variance explained by each component, and the right plot shows the cumulative variance explained. And the rule of thumb is that you keep components until you reach 80 to 95% of the cumulative variance, or you can look for an elbow in the Scree plot where the explained variance suddenly drops. Okay, so here what we are doing is we are plotting the percentage of variance explained by each principal component. So we are multiplying by 100, so that's the percentage of variance explained, and yeah, the Scree plot here. Alright, so this subplot command is used to plot 2 plots side by side. So 1 by 2 means there is going to be a grid of 1 row and 2 columns when you make the plots, and then 1 to 1 means that you are looking at the first plot, and then 1 to 2 means you are looking at or you are trying to make the second plot. Okay, so as we discussed, the first plot or the left plot, it shows the explained variance, and then the second plot shows the cumulative explained variance. So that's why we are using np dot cum sum. So that's the cumulative sum command. Okay, so you can see the plots here. Alright, so the left plot, like I said, is the Scree plot. The percentage of variance, this is principal component 1 with the highest variance around 75%, then this is principal component 2 around 20% of the explained variance, then the principal component 3 is only around 20%, only about 5% here, so that's PC3, and then finally this is PC4. So I hope this makes sense to you, and you can also look at what is happening here in the cumulative variance explained. Obviously the cumulative variance is going to reach 100, right, when all the principal components have been exhausted, but then you can see that the first two principal components explain almost 96% of the variance, so the third and fourth principal components they are not necessarily needed, and even in the Scree plot you can see that the percentage of variance explained is just dropped considerably beyond the first two principal components. Okay, so now that we do have the principal components, we can visualize, right, different component pairs, and each point will represent one sample in the reduced space, right. You can plot, for example, the data points in the space of PC1 versus PC2 or PC3 versus PC4 and so on and so forth, and in this case the colors represent the flower type, and like I said, we already know these in this case. However, that will not always be true, right. In real life applications or real world applications of unsupervised learning, you may not know the types, right, of the clusters a priori, right. So that's what I have mentioned. So do keep in mind, whatever core engineering application you are applying this to, that you may or may not know the classes a priori. Alright, so the first few components, they capture the most variance and often show clear patterns, and then the later components, they capture less variance but may reveal subtle relationships. Sometimes it's just noise, right, in the data if you go to very lower components. So let's examine the different component pairs to understand the structure of the data set. Okay, so here we are visualizing the results for PC1 and PC2, and what I am doing is I am plotting the training data as well as the test data. So this plot is showing you a scatter plot of the train PCA, right. So 0 is the first component and then 1 is the second component. So remember, in Python the indexing of the arrays, it starts from 0, and that's why 0 is the first component and 1 is the first component, and yeah, I am using the already known y values, right, the type of the flower to show the colors, right, but in reality you may or may not know this. Alright, so that's for the plot, right, between PC1 on the x axis, right, and PC2 on the y axis for the training data, and this second plot is the PC1 versus PC2 for the test data. Now what I have also done here is, instead of plotting PC1 versus PC2, I directly plot the first feature and the second feature. So this is the first feature, and this here is the second feature. Okay. So this will be interesting because we are gauging the utility of PCA, right, just by looking at the features themselves versus by looking at the data points in the PC space. And similarly, I am plotting the test values of the first feature and the second feature. Alright, so if you want to recall, right, you know that the first feature is the sepal length and the second feature is the sepal width. Alright, so let's go ahead. So what do we see now? So what we see here is this, right. So there are 4 plots. The top 2 plots are PC1 versus PC2, right, PC2 versus PC1, PC2 with the explained variance of 0.22 on the y axis and PC1 with the explained variance of 0.74 on the x axis, and you can see that the points are already sort of segregated into different types of flowers here, right. So this is one type here, this is another type here, this is a third type. So PCA has demystified your data set by revealing the relationships between the points, right. So you are able to immediately figure out that there could be 3 different types of flowers here, since this is a data set on flowers. But now look at this. This is the data in the feature space of the original features, right, in the space of the original feature. So that's a plot of feature 2 versus feature 1 for the training data, feature 2 versus feature 1 for the test data. And look, you can't make out really any patterns whatsoever. Just compare the plots on the top. That's the data points in the PC space, right, PC2 versus PC1 space, whereas this is the same data in the original feature space. I cannot make out any sort of pattern in the original feature space, but I can see a lot of clear patterns here. There's one set of points here, another set of points here, and then a last set of points here. Although one could say that, look, these two clusters you can't really make out that that's true, but at least the first set of points from these other points, that's something which actually the PCA has told us. So this is where the unsupervised learning really shines, right? It reveals the underlying structure of your data set. All right, and don't worry, I mean, we will give you the notebooks, right, Jupyter notebooks associated with the all these commands. So if some of these commands are cut off, then you need not worry about that. Just try to understand this, and then you can try to work with the notebooks. All right, so that's in the space of PC2 versus PC1. Now what happens if we plot the training data and the test data in the space of PC4 versus PC3, right? So that's what we are doing here. So this is PC3, this is PC4, and we are trying to plot the data points as PC4 on the y-axis versus PC3 on the x-axis, and we are doing that both for the train and the test data, and this is what we had done earlier as well for PC1 and PC2, and the results are here, right. For these principal components, PC4 which explains 1% of the variance, and PC3 which explains only 4% of the variance, you can see that clearly not much information is revealed if you start plotting the data points in the space of the later principal components, right. So this is just illustrating that the utility of the principal components goes down and down and down as you go down the less and less explained variance. All right, so the key insight from the above plots regarding the importance of the later principal components is that the later components explain progressively less variance in the data because the first few components capture the major patterns and relationships. The later components, on the other hand, can often represent noise or only minor variations which may not be very interesting or useful in some cases. In other cases it may be important. So it's on a case to case basis you have to see this, and obviously there are diminishing returns. Every subsequent component adds less new information as long as you have ordered them in the order of the decreasing eigenvalues of the covariance matrix of this scale data, and one can often just use the first few components for most applications. Okay, so I hope this gives you an idea of how principal component analysis can be useful in a certain use case, and I encourage you to think about examples from your own engineering disciplines, whether you are trying to cluster the structure of molecules in a drug company, or the structure and properties of materials if you are in a battery or company working on solar cells, or if you are in a production plant where you are trying to cluster the quality of the products that are being made in terms of what were the plant or operating parameters on that day. So these kind of things, it's really sort of field specific, so I encourage you to think about more and more examples. So now what we will do is we will proceed on to k-means clustering, right. This is the simplest clustering algorithm, and this is all about partitioning your data into k different clusters, right, based on the centroids or the means of every cluster. The theory behind this we did clearly in the class. So now one thing to be kept in mind for each of these algorithms, obviously there are inbuilt codes in Python which do these, but I encourage you, if you're interested and even otherwise, to write some of these codes yourself in Python or C++ or even MATLAB, and often it will give you a lot of insight into how these algorithms really work. Of course, in class we are taking some examples wherein we are doing through pen and paper some of these, but you should also try to implement them onto a computer for increased proficiency. So like I said, here we are splitting the data into k clusters, but what value of k should we use, right? That's an important question that needs to be answered. So k-means clustering is the simplest form of clustering in machine learning, and the algorithm can be used to determine if there are similarities between certain points in the data set. So this divides data into k clusters and minimizes what we had studied in class, which is called the within cluster sum of squares. And because it works on the principle of a centroid, right, and the distance to a centroid, what's going to happen is it will result in roughly spherical clusters of similar size. Now if you want to work with non-convex, non-spherical sort of clusters, then we have to use other more complex clustering algorithms like dbScan, which we will also discuss. So as discussed in the class, the elbow method helps to find the optimal number of clusters. So wherein you plot the within cluster sum of squares WCSS versus the number of clusters and look for the elbow where additional clusters don't significantly reduce the variance, the within cluster sum of squares, and then that's obviously a balance between the complexity and performance, right? If you have too many clusters, then obviously you're not learning much. If you have too few clusters, also you're not learning much. So for large data sets, it can become important because the algorithm could be slow. So again, implementing it in Python is very easy. There are inbuilt functions, but you should try to do this on your own. So here specifying the random state, important for reproducibility, and then the number of clusters we are trying to vary from 1 to 8, right? 1 of course means that all points are in one cluster. Alright, so we are plotting here the number of clusters, right, versus on the y axis the WCSS. So you can see that the within cluster sum of squares is tapering off. This is the elbow plot, and you can use this to determine that the optimal number of clusters is say 3, right. And you know, in this data set, in this specific case, you already know there are only 3 types of flowers. So yeah, I mean this is not very useful here, but for more complex data sets wherein you don't know the underlying number of types of data points, clustering can be very useful. Alright, so based on the elbow plot, we choose k equals 3 as it appears to be the optimal number of clusters. So let's now analyze the distribution of clusters. So how many points are there in each cluster, what's the centroid of every cluster, and the final within cluster sum of squares, right. So we are applying k-means with k equals 3. So in this case we know the iris data set has 3 species. Okay, so first we have to fit predict. So we have to find the cluster centers, right. So that's what is happening here, and then once the cluster centers are known, right, any new points, right, which is what we are doing with the test data, you for every point you can find out which is the center to which it's nearest, right. So let's say that there is a new data point that you have, right, somewhere in feature space. You can find the distance of that point from, let's say, the center 1 cluster, center of cluster 1. You can find the distance of that point from the center of cluster 2, and you can find the distance of that point from the center of cluster 3, and you will assign the point to that cluster, right, which is the closest to it. So in this case, for example, if C1 was slightly longer, the way I have drawn it, it's almost equal, but still the k-means algorithm will give a result, right. It will tell you that the point is close to one of the clusters. So that's how an assignment can be made for new data points. So you are learning here not only how to find the cluster centroids using fit predict, but also if a new point arises, how you're going to put it into a cluster. Okay, so these are the points in every cluster: 32, 33 and 40 in the test set, and then in the train these are the number of points in every cluster which we are doing through this bin count on the train clusters and the test clusters, and this is available in the NumPy package. And finally, we can now visualize the data set that was generated through k-means, right. There is a plot in feature space, right, the first two features, the sepal length and width, and then we also can do the plot in the PCA space, and this is something we had done after PCA as well, and now we are doing that after k-means clustering. Alright. So those are the two types of plot, the feature space plot and the PCA space plot. We can also do it in the target space plot, right. So target classes here are the three types of flowers, so you can see in that space as well. Alright, so let us go ahead and do this. So here we are defining the colors and the labels of the species. There are three types of flowers, setosa, versicolor and virginica, and we are assigning them colors teal, purple and gold here, and there are various subplots we are making, three different subplots. Like I said, the first is the original features, right, and we are looking at the points belonging to cluster 0, cluster 1, right, and then we are plotting the data points, and then similarly this is being done for the PCA space as well as the original true species space. So what do we get here, right. So these are the three plots. This is in the clusters in the original features. So clearly you can see the first cluster looks different, but there is some intermingling of the second and the third clusters. In the PCA space, again, I mean, similar things are happening. However, one could it's difficult to say that these two clusters are different. And finally in the true species space, right, versus PC1 and PC2, these are the true, right, flower types. You can see that these flowers here, right, these are being partitioned into the third cluster here. So the points here, right, which truly are of the versicolor type have been put into cluster 2, which is actually right, having some points that should have been classified as versicolor, but here by looking at it you would say that they are part of the virginica cluster. So obviously unsupervised learning is not flawless, it can make mistakes like it is happening here, but nevertheless it is useful to understand the underlying structures. At least you can see that setosa is very different from versicolor and virginica type of flowers. So this brings me to the end of this tutorial. Today we looked at unsupervised learning in Python. Specifically we examined the use of principal component analysis for linear dimensionality reduction as well as k-means clustering for dividing the data set into various clusters. We saw that we have to use a standard scalar, and then this must be done on the trained data, and then the same scalar should be applied to the test data. And similarly when you are doing clustering, you can find out the cluster centers with your training data, and then for any new data you can use the cluster centers to assign them to a certain cluster. So I hope you learned something new today about how to implement unsupervised learning. I look forward to seeing you in the next class as we continue this tutorial. Thank you.